This is Aryan from EDD Academy, and today we'll be going over related rates. So related rates are always going to be a word problem. So the very first thing you're going to want to do is find an equation from that word problem. Then you will take the derivative with respect to time of that equation, and then you're going to want to make sure that there is only one unknown, either by solving the equation or otherwise manipulating it. And then you're going to solve for the unknown, which will probably be asked for in the word problem. So let's start with a pretty simple, pretty basic problem. Here we have a circle whose area is expanding at a rate of 20 pi centimeters squared per second. And I want to know how fast is the radius growing when the radius is 5 centimeters. So basically what we're doing is, if I can illustrate, here's a circle, and we want to be able to relate the rate at which its radius is growing to the rate at which its area is growing. So the very first thing to do, if you remember the steps, is to define the area with, given the radius. So this is an equation we should all know. It's a equals pi r squared. And from here we will take the derivative with respect to time. Now something very important to remember here that's often glossed over with related rates are that all of these variables, a and r, are functions of time. So really it's a of t equals pi r of t squared. But usually we don't write out the t and parentheses because it's just a waste of time, and we just remember that these are functions of time. But that is something important to remember. So now we're going to take the derivative with respect to time of a and of the quantity pi r squared. And this value, the derivative of respect to time of a is dA dt, and of pi r squared is, you can always take the constant out, so pi times 2r dr dt. And here we want to look at what we have, or what the word problem has given us. We know 20 pi is the rate at which the circle's area is expanding, so that's dA dt, right? It's the derivative of a with respect to time. And the radius is 5, and that's r. And what we're trying to figure out is how fast the radius is growing, so that is dr dt. So let's plug in what we know we have, which is 20 pi equals pi times 2 times 5 dr dt. And then we can solve for dr dt to get 20 pi over 10 pi, and further to get 2. Now what are the units here? Because units are very important in word problems, always. So the way we do this is it's the derivative of r with respect to time, r over t. Units of r are centimeters over units of time are seconds. So the final answer is 2 centimeters per second. So here we have a slightly harder problem. The radius of a spherical balloon is increasing at a rate of 2 centimeters per second. Find the radius of the balloon when the volume is increasing at a rate of 32 pi centimeters cubed per second. So once more, we're going to start by writing out the equation of the volume of a balloon given its radius, or of a sphere, a spherical balloon. So that is V equals 4/3 pi r cubed. And then we're going to take the derivative with respect to time of both sides of this equation. So that's ddt of V equals ddt of 4/3 pi r cubed. And once more, we have 1 times dv dt equals 4/3 pi. You can always take out the constant, times 3 r squared dr dt. And now we can simplify this a bit. Dv dt equals 4 pi r squared dr dt. Now let's take a look at what the word problem gives us. So here it tells us the radius of a spherical balloon is increasing at a rate of 2 centimeters per second. So this must be dr dt because it's 2 centimeters per second. And then we're looking for the radius, so we're looking for r. And the volume is increasing at a rate of 32 pi centimeters cubed per second. Centimeters cubed per second, so that must be the volume. So we have dv dt, we have dr dt, and we're solving for r, so we're set. We have 32 pi, we're just going to plug everything in, equals 4 pi r squared times 2. If we solve for r squared, we get 32 pi over 8 pi, which equals 4. And take the square root, we get r equals 2, and the units here are fairly straightforward. The radius is clearly measured in centimeters. So here we have a problem in which a 13-foot ladder is resting against a wall, and if the bottom of the ladder is sliding away from the wall at a rate of 6 feet per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 5 feet from the wall? So this is a pretty convoluted question if you've never worked with related rates before, but I promise you ladder problems always come up either in the AP Calculus exam itself or in normal class exams when it comes to derivative applications. So this is a format you're definitely going to want to be familiar with. And the way I like to start off these types of problems is by illustrating. So here we have our wall and the ground and our ladder, which we know is going to be a constant 13 feet. That will not change. That's not one of the variables. But what can change is the distance between the wall and the ladder and the distance above the ground that the ladder is. So I'm going to call the ground the x-axis and the wall the y-axis, and then call this distance right here x, and call this distance y. And the rate at which x is changing, or how fast the ladder is sliding away from the wall, is of course dx dt, and the rate at which y is changing, or how fast the ladder is sliding down the wall, is of course dy dt. And we know x is 5 from the question, and that dx dt is 6 feet per second. So we know this, and we know this. Now let's look at an equation for this drawing here. So this looks like a right triangle to me, and if we recall the Pythagorean theorem, we know that a squared plus b squared equals c squared. If we substitute in our own variables here, we get x squared plus y squared equals 13 squared. And of course, we're going to want to take the derivative with respect to time. So d dt x squared plus d dt y squared equals d dt 13 squared. And this is 2x dx dt plus 2y dy dt equals 0, because 13 squared is just a constant. And now we look at what we have and what we don't have. Once more, we have 5 for x and 6 for dx dt, but we don't have y or dy dt. So how do we get around this? Well, we're not going to find dy dt right off the bat because we're solving for it, so let's look for y. And the way we would do this is by taking a look back at our Pythagorean equation here. So we know that at this point in time, the ladder is 5 feet away from the wall, so x must equal 5. And from that, we can figure out what y is, because 5 squared plus y squared must equal 13. Remember, we just plugged in 5 for x. And now we know y equals 12. Now we have everything except for dy dt, so we can plug that in. 2 times 5 times 6 plus 2 times 12 times dy dt equals 0. And now we will solve for dy dt. So we get dy dt equals negative 30 over 24, which is negative 2.5. And when it comes to units, we're looking at y over t. Y is feet and t is seconds. So it's negative 2.5 feet per second. And that about covers it for related rates.